All right, everybody, welcome to the video here for lesson number 10 on the fundamental theorem of algebra. Now, before we actually discuss this homework assignment, I just want to go over what the fundamental theorem of algebra really is. So looking at a problem here, in your notes, we have this setup. It says the fundamental theorem of algebra says every polynomial function of a degree of 1 or greater with real coefficients has at least one complex zero. So what that means is we can have 1 0, 2 zeros, 3 zeros. And remember, when we see the words complex zero, real zeros are also complex. Like this is a complex zero. This is a real zero. Notice there's a 0i here. This is a 5i. All right. So we still have complex numbers even if it is a 0i, just so you know. The bigger reason why all of that works is complex numbers is like the big circle that encompasses everything. So complex numbers is here. Inside complex numbers, you have the real numbers. So all real numbers are really complex numbers. Inside the real, you have rational and irrational, and you can go with that. Okay, complex numbers have both real and imaginary parts. So imaginary numbers are kind of its own little bubble within the complex number bubble. Okay. So with that said, let's take a look at our homework. So in number one, it gives us this fifth degree polynomial, and it says not to factor this. So we actually don't even care what these solutions are. I just want to kind of go over the theorem of algebra here to be able to see how to answer these questions. So it says how many linear factors of p is p guaranteed to have? Well, if it has 5 zeros, it has 5 factors. How do I know it has 5? The degree of the polynomial is 5. That's the largest exponent. So the answer is going to be 5, and that is because the degree is 5. How many real zeros does P have? Well, real zeros, those are the x-intercepts. There are 1, 2, 3 x-intercepts. So there are 3 because there are 3 x-intercepts. Now, if there are 3 real zeros, that means there are going to be 2 complex zeros. And then what do we know about these complex zeros? They are always conjugates. Don't know what they are, but I know there's 2 of them, and I know they're going to be conjugates of each other. Okay. Number 2 says to actually find the zeros of a function. So here's some crazy function, and it wants us to find the zeros. The first thing I'm going to do is I'm going to figure out what's the degree. So I have 2, 4, 7, 8, 9. So this is a degree 9 polynomial, meaning there should be 9 zeros. So for x squared plus 4, after the last few lessons, I hope you already know the answer to that one. But if you don't, it's totally fine. So let's do some factoring here. So p of x is equal to x plus 2i, x minus 2i, x plus I, x minus I. Oh, look at that. That's a throwback question. X minus 2 and x squared plus 2x plus 4. Where did I have to get that from? That's the difference of 2 cubes. The last 2 are already factored, so that's 2x plus 3 and 3x minus 4. Now, out of all of the factors I've just created, one of them, I don't want to say is not factorable over the complex numbers. It's just kind of difficult to do. So this one we're going to use the quadratic formula for. So the discriminant is 2 squared minus 4 times 1 times 4. So that's 4 minus 16. So negative 12. So if I do the quadratic formula, I'm going to get negative 2 plus or minus the square root of negative 12 all over 2. The square root of negative 12 can be simplified, so that's going to become a 2i square roots of 3 all over 2. And then we can say this is negative 1 plus or minus I squared root of 3. So I already know 2 solutions, or 2 zeros, of this equation right there. The other ones I can get just by doing our regular zero finding. So x plus 2i equals 0 is going to give me x equals negative 2i, x equals positive 2i, x equals negative I, x equals positive I, x equals 2, x equals negative 3 halves, and x equals positive 4/3. So what is this big final answer going to look like? So I'm going to say x equals, I like to put all the real numbers first. So I have negative 3/2. I have positive 4/3. I have 2. Then I'm going to put the imaginary numbers next. So I have 0 plus or minus I, 0 plus or minus I square roots of 3, and then 0 plus or minus 2I. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 solutions. If you count them up, just to double check. Notice out of your 9 solutions, only 3 of them are real. So that means this graph, even though I have no idea what it looks like, is going to have 3 x-intercepts. Also, since it's a degree 9 polynomial, I know it's going to start like this, it's going to do something in the middle, and it's going to end like this. So I already know a lot about this graph just by looking at the degree and what the zeros are. I could totally type it in my calculator and try and graph it if you want to. That's kind of overkill though. Okay, moving along. Number 3 gives us a polynomial. I hate that the printout did this. Those should have arrows on it. All right, so we have consider the polynomial p of x is x to the 4th. So this is quartic. So that tells us I have 4 zeros. Out of the 4 zeros, 1, 2 of them are real. So negative 1 and 3. So the real zeros are negative 1 and 3. How many complex zeros must we have? 2. And the reason why is because it's a degree of 4. So I have to have a total of 4 solutions. Then it says factor p by using the zeros of the graph. So if I use my zeros, I can factor out one of the factors. So negative 1 is a 0. If I put 1, negative 6, 11, and negative 18, no, there's a 0 there. 0 and negative 18, right? 4, 3, 2, 1, 0. So we're missing this 0x term. So if I bring down the 1, I have a negative 1. That's a negative 7. Multiply that across. I have 18, negative 18, 18 negative, and then positive 18, we get a 0. We want zeros. Zeros are good because that means that that really truly is a factor. That's also a quick way of checking and verifying that that's actually a solution, right, without having to plug it in, okay? So what does that mean? That means p of x is really the two factors x minus 1 and x cubed minus 7x squared plus 18x minus 18. Now, I have another 0. That 0 of 3 is still part of the factors here. So if I divide that out by 3, so if I put a 3 here in my synthetic division and go 1, negative 7, 18, and negative 18, no missing terms this time. The 1 comes down, I have 3, negative 4, negative 12, 6, 18, and 0. So now I know p of x is equal to the two real factors, x plus 1, x minus 3, and this new factor, x squared minus 4x plus 6. Now that new factor that we have there is factorable, but that's not what it's asking us to do here. It just says factor p, right? So if I factor p, that's factored as much as I can without having to get kind of crazy here. It doesn't even say linear factors, so that's factored, right? Now, if this did say linear factors, we can show that, and I'll show you that after we find the zeros. So we already know 2 zeros. We know 1 0 is negative 1. We know another 0 is 3. The other 0 is going to come from this quadratic. So the discriminant here is negative 4 squared minus 4 times 1 times 6. So if I do that, I get negative 8 for my discriminant, telling me that that's going to have complex zeros. I already knew that though, because the graph only crosses the x-axis twice. So if I plug into the rest of the quadratic formula, so I have negative of negative 4, so positive 4, plus or minus square root of negative 8 all over 2 times 1. So I have x equals 4 halves plus or minus square root of 8 Square root of 8 is 4 times 2, so that's 2 square roots of 2. So that's going to be 2i square roots of 2 all over 2. Or x equals plus or minus 2, 2 plus or minus I square roots of 2. So there's all your zeros, right? So I have another set of zeros here of 2 plus or minus I square roots of 2. You can leave them separate like that or put them in one big bracket. It doesn't matter to me. So what does this mean? This means P of x can be written in even a better factored form of x plus 1, x minus 3. And then if you take those two complex zeros, subtract 2 and subtract I squared of 2 or add I squared of 2, I'm going to wind up getting x minus 2 plus I squareds of 2 and x minus 2 minus I squareds of 2 for all of the factors. So that actually would be the best possible answer for this question. But you'd have to do part D before you could do part C. Hopefully this video helped. Notice this is the end of the chapter, so you're going to have a quiz coming up in a day or two here. So just keep that in mind. Check the board for what day it is. Also start working on your study guide, right? There's a lot of material in this chapter, right? This chapter covers everything from systems of equations to imaginary numbers, all the different things about complex values and zeros. It's kind of a culmination of everything we've been doing, right? So keep working on that and we will be good. All right, keep studying and we'll be good for our test coming up. See you later.